Welcome everybody to the scheduling seminar. And today we have a talk by Leah Epstein from University of Haifa. Leah is with Department of Mathematics, the same university. And she is interested in scheduling and load balancing and bin packing problems. And she likes to read belletry and books. So if you will be lucky, she will recommend you some good book to read. So Leah, please go ahead.
Thank you. So I'm going to talk about the benefit or the power of preemption. And maybe I will discuss some easy stuff, but I would like I would like to try to give a talk that everyone can understand. So here is the plan. We would like to, in this kind of problem where we're interested in the benefit or power of preemption, we would like to compare two types of schedules. And each time that we compare it for the same input. So I'm going to show you the definitions that we need, and then some examples and simple proofs that you may or may not be familiar with. And the goal of this talk is to understand why we think that one model is easier, even though I recently, I will not include it in the talk because it's not ready, but I recently encountered the problem where the preemptive case seems to be harder. And there are other problems like that. But the problems that we analyze here, the preemptive case is easier, and we will maybe we will get an intuition of why this is the case. And this will lead us to an understanding of why the problems are attractive, at least in my opinion. So, of course, this slide is not very useful for a scheduling seminar, but since it is a bit confusing that we study two problems that have the same input, let me remind you that the scheduling problem consists of jobs and attributes, where attributes are usually the size, the processing time of a job, and maybe a release date, that you cannot start the job before that time. Then you need to know how many machines that you have and which types they have. And they can be just one machine or identical machines or machines with speeds that are called uniformly related. And then we need an objective, what we want to usually to minimize. At least in this talk, we discuss minimization problems. So it could be the Makespan, that is the last completion time, or total completion time, or total weighted completion time, or something else like a norm of the completion times of machines or of jobs. And the crucial part is what counts as feasible, whether we allow preemption or not. Okay, this is very simple illustrations of jobs. Usually look like this, and a job has a size or a processing time on a unit speed machine. They are indexed just 1, 2, 3 up to n. In order to assign a job, we must assign it to run completely. So if the schedule is non-preemptive, it receives a continuous time slot. If there are multiple machines, it has to be on some machine, and we need to specify the machine and the time. And in a preemptive schedule, we still have to execute the job completely, of course, but we can split it into parts, and these parts are assigned separately and independently, but they cannot run at the same time because we don't run them in parallel. And we, as I said, we have machines, and the machines in this case, I only discussed the very elementary problems today. So machines are available starting from time 0 until we don't need them anymore. And many of the problems can be generalized in many ways. Every machine can process just one job at a time. And as I said already, we cannot run parts of one job in parallel. And also we don't have resource sharing. So parts of jobs don't have epsilon sizes. They're split into reasonable sizes. So the illustration for one machine is drawn in the bottom. Consider, you see there's a time axis, and it is horizontal. And in this case, there is a job of size 3, so it consumes 3 time units and can't run anything in parallel. And for parallel machines, I prefer the other axis. So we could have a long discussion of which is better, but this is the way I'm used to doing it. So it's just the same, but you have multiple machines, and every job is assigned to some machine, to some time slot. If it's non-preemptive, if it's preemptive, you can split. For uniformly related machines, there are also speeds. So what you see are not the original sizes of jobs, but the sizes divided by the speeds. So for example, for the first machine is of speed, it has speed 3. The job has size 3, so it consumes just 1 time unit, and so on. So here is a comparison between preemptive and non-preemptive in terms of definitions. In a non-preemptive schedule, every job is assigned to one machine and to one slot, to run completely in this time slot, and it runs continuously or consecutively. In a preemptive schedule, it can be split into parts, and each part is assigned separately. And there's also a model of fractional scheduling where you do allow to run parts in parallel, but this is not what we are going to discuss today. For that to become interesting, the model needs to be slightly more complicated. So here is an illustration of the differences. On the left-hand side, the assignment is fractional. So if we just have one job in this case, we can split it equally and have a flat schedule. If the schedule is non-preemptive, we cannot split it, and we cannot split into parts. To run them in parallel or not in parallel, we just can't split it, and this is what you see in the middle. On the right-hand side, you see a preemptive schedule. For one job, it doesn't help because you still need to run it, and you cannot run it in parallel. So if the job has size m, and m is the number of identical machines that you have, the schedule on the left-hand side has Makespan or last completion time of 1, and the 2 others have m. So here it doesn't seem to be helpful to use preemption. And on the next slide, you can see that preemption does help if you have more jobs. So in this case, you have 3 jobs, each one has size 2. And in this case, if you cannot split jobs, by the pigeonhole principle, you're going to have 2 jobs on the same machine and completion time of 4, or at least 4, because you could use idle time. And for the preemptive schedule, you can split the light blue job into 2 parts. You can see it on the left-hand side. And then if you assign them carefully, the completion time is free for everything, the Makespan. And it could also assist with sum of completion times or whatever. But here the example is for Makespan. Okay, many definitions, but I just need one important definition for this talk, which is the benefit or power of preemption. So we measure how much allowing preemption can reduce the cost of solutions. So for all problems that we consider, it will be the case that if preemption is allowed, it doesn't mean that you need to use it. So every non-preemptive solution will also be a preemptive solution, but a preemptive solution could be different. It can split jobs. So we compare an optimal preemptive solution and optimal non-preemptive solution for the same input. You can see the big formula 3 lines from the bottom. Let me, this one. So in this formula, we compare the cost of an optimal solution that cannot preempt. The N is for non-preemptive, and an optimal solution that can preempt for the same input I. It cannot be smaller than 1 because of what I just explained, that the non-preemptive solution is also seen as a preemptive solution, but it could be in principle much larger, or it can just be 1 for some problems. For other problems that are probably less interesting, it can be infinite. It's difficult to go to the next slide. Okay, so the attributes that we need for now of jobs are weights. So every job has a weight, let's say non-negative. Release date, as we already discussed, time that you cannot run them earlier. And we also want to say something about the objectives. So in this slide, we compare 2 schedules. You can see that in the top one and the bottom one, there are 2 jobs. There's no preemption. And there are release dates, so we can't start the first job before time 2. In the top schedule, we just wait until time 2 and then run it, and then afterwards we run the other job. In the bottom schedule, we decide that since the release date of the second job is 1, we swap them and can run them earlier. And my question is, which schedule is better? Maybe it's a better question for students, but still. So the next question is better in terms of what? If we are interested in the Makespan, then the top one, you can see that it finishes later, so the bottom one is better. Then we can compute the total completion time, the sum of completion times, which is 12 in the top, 7 plus 5, and less in the bottom, 6 plus 3, 9. So it seems that the bottom one is winning. But then if you add the weights, then suddenly the top one can win, because you maybe not always, but here you can add the weights in the way that you want, and you end up with a better schedule on top. So when we compare schedules, it also depends on what we are trying to achieve. Here's some more notation because I'm going to start to talk about something that is also maybe well known, but already slightly more technical. So we have an input I, M machines, and jobs. Capital P is the total size of jobs, and the lowercase q is the maximum job size. So what can we easily say about both preemptive and non-preemptive schedules, because we cannot parallelize, or a single machine, the machine can anyway run just 1 job at a time. The Makespan is has to be at least P, the total size of jobs for 1 machine. If there are, in the next bullet, if there are M identical machines, you once again, pigeonhole principle, the Makespan is at least the total size divided by the number of machines, but also at least the largest job. If now the third bullet, if the machines are uniformly related, the Makespan is at least the total size divided by the sum of speeds, because the averaging here is different. And it is also at least the largest job divided by the largest speed, because it has to be executed. So I'm going to talk about Makespan. And then afterwards about unweighted and weighted completion times. For Makespan, these are more classic results, but whoever is not familiar with the model may be interested in that. Afterwards, the results are not really new, but at least not as old as the ones from Makespan. So this is, the slide looks pretty bad, but it is a very easy algorithm. I'm just trying to say that if you minimize Makespan on one machine with release dates, it is easy because you sort them and assign every job at the earliest time possible. And this algorithm is optimal, as you probably know, because of the last part. All the three last jobs have release dates. In this example, on slide 16, they all have release dates of 9 or more, so we cannot complete them before time 16. So why am I discussing something that is so well known and simple? The reason is that in this case, preemption does not help. And according to our definitions, it means that it is optimal for both preemptive and non-preemptive, and there's no benefit to preemption. So this was pretty boring and a bit discouraging. But if we move to Makespan on a machine, multiple machines, things are not as easy. We skip the release dates. We even don't have weights, maybe because we are doing Makespan. But already it is not as trivial. The tight bound on what? On the benefit of preemption. For uniformly related machines, this is like the fifth line of the slide, is 2 minus 1 over n. And one can improve it if you have equal speeds or identical machines. That's in the middle of the slide. If you check the numbers for our two machines, you see that you get 1.5 and 4/3. So one question that we can ask is, how can we obtain an optimal solution? Why do we need an optimal solution? The reason is that we are going to compare an optimal solution for one variant with this, and another variant with the same input. For that, you would need to know what an optimal solution acts like. Only these problems are frequently NP hard, so it's not so easy to know what an optimal solution does. Its structure is not nice. It's not really an algorithmic problem, but still, if you have an algorithm, it makes things easier. So for these specific problems, the non-preemptive problems are NP hard, but the preemptive ones are not. For the preemptive problem on identical machines, there's a very old algorithm of McNaughton, and it is so easy that even my students understand it. So what it does is to compute the bounds on an optimal solution, which is the average completion time and the largest job, and this is actually the optimal completion time. Let me show you in a figure how it works. So you can see the figure here. You don't even need to sort the jobs. You just start from the first machine, assign the jobs. When you don't have space for the next one, you continue on the next machine. And the line that we draw here, and here it is at 9, is the maximum of the two bounds, two lower bounds and an optimal cost, optimal Makespan. So you can see the job 4 moved from the first machine to the second one. We assigned it first on the first machine, but in the schedule, it actually runs on the second machine first. So here, the interesting part for us now is that not the algorithm, but that the bounds give you the exact optimal cost for preemptive schedules. Here is the lower bound for identical machines. It is very simple. It's a generalization of the one that I showed you earlier. If there are n+1 jobs in a non-preemptive schedule, 2 jobs have to be on the same machine. And in a preemptive schedule, you can apply McNaughton's algorithm. You can see it on the left-hand side of slide 21. And this is what gives you this ratio of 2m over n+1. So the question is whether this simple construction is tight. So I did not calculate the numbers exactly, but you can see that on the right-hand side, you just need to run 2 jobs. On the left-hand side, you can have a completely flat schedule. The upper bound is going to be shown using an algorithm. So you can ask why we are using just a greedy algorithm for the analysis. But if we are showing an upper bound, and the output of an algorithm is fine as long as we manage to prove the correct bound. So it is easy and has a simple structure, and this is why we use it. The algorithm is LPT, you probably know it. We apply list scheduling on a sorted list of jobs. And okay, we don't need the examples, but I wanted to include all the slides because they are published, and if students want to look into it, they can see the examples. So here's the analysis. We would like to say that the number of jobs is at least n+1. But this is, of course, where m is the number of machines, but of course it does not need to hold in general that there are at least n+1 jobs. Let me remind you what we are doing. We are proving now the upper bound on the power of preemption for identical machines. So if there are just m jobs, no matter whether you use LPT or an optimal solution, you get a schedule that looks like the one on slide 24. There's no reason to assign the jobs. There's no reason not to assign the jobs to different machines. This is what I wanted to say. So this is an optimal solution and an interesting case. The maximum completion time, the Makespan, is just the largest job, the size of the largest job, which is Q. Otherwise, we consider schedules with at least n+1 jobs that are more interesting. This is doesn't matter which version of LPT you use here. It's the same for identical machines, so we can discuss it. Just one comment that we assume that the maximum completion time is of the last job. Because if there are further jobs, you can just remove them. They don't change the output of the algorithm. And let me remind you that even though we are considering a mathematical concept, we do it using an upper bound based on an algorithm. So we assume that the largest job is, sorry, not the largest job, the largest completion time is of the last job. And remove the rest. And this is what I'm going to assume all the time. I see that Tammy had a question. The fragments don't have to be integers. And it is not very important that the sizes are integers. Okay. So let's continue. So we denote by P, these are the 2 last lines of slide 24. P is the last job and its size. And since we applied LPT and we assume that the last job is the one that determines the Makespan, we know that all other jobs are not smaller or larger. So P is the smallest size. Here is what it looks like. Maybe not the perfect picture because it looks here that P is large, but still this is an illustration. We end up assigning a job P. It is assigned by LPT, which means that all the brown parts that may contain several jobs, that they are not smaller than the brown part before P. I is going to be the machine of P. All right, so we know that there are at least n+1 jobs, including P, because we already checked the case of m jobs or less. And I, as I said, is the machine of P in the schedule. And I use X sub K for the completion time of machine K for every K, which means that Xi is the completion time of machine I, only I excluded the job P, so the actual completion time is L, which is Xi plus P. Let me show you the illustration. Here it is. So ignore the purple jobs for a second. L is what we're interested in, the completion, the last completion time, the Makespan. We go back. So we know that for every machine, it's machine K, X sub K is at least Xi because of the greediness. And then what we do, let me go back to the illustration. We add an artificial purple job to every machine that has the same size as P. So now all machines have completion times that are the original Makespan or more. And what we do now is just some calculations. So we have P prime, which is the total size together with the additional jobs. And with some manipulations, we find the formula here. The upper bound on L. L was the Makespan for LPT. And what we are going to do, we need to compare it with the optimal cost for a preemptive schedule, because we are looking for the benefit of preemption. So we find some bound, not some bound, the one that we need for the preemptive schedule, divide the one for the non-preemptive by the one for preemptive, and end up with what we were trying to prove. And this was for identical machines. Now I would like to move to related machines, uniformly related ones. Luckily, there's also an optimal preemptive algorithm for that. Or actually, there are many of those. You have a list on the fourth line of the slide. Unfortunately, they are slightly more complicated. But still, it is convenient to use an optimal solution. So we assume here that the jobs are sorted by non-increasing size. And also, we assume that the number of jobs is at least the number of machines, because if we have more machines than jobs, we can just remove the slowest ones and we don't need to use them. This is because we cannot run parts of jobs in parallel. So we have the jobs sorted from largest to smallest, and similarly, here on slide 30, we also sort the speed from largest to smallest. And then there is a formula known for the Makespan. Only unfortunately, or maybe fortunately, here it consists of m different bounds and the maximum of those, and not just two, like for identical machines. If you try to plug in the speed for identical machines, which are all ones, unit speed, you will just get the old formula. So it is convenient to have at least a formula for one of the models, and for the case, the non-preemptive case, we will not have a formula because that is an NP-hard problem. So we will have to do something else, maybe once again analyze an algorithm. So I think most of you already know this, but the idea is here to consider not only the largest job divided by the largest speed, but also two largest jobs divided by the sum of the two largest speeds, and so on. And like we continue like that up to m-1. So the m-1 largest jobs divided the sum of these jobs total size divided by the m-1 speeds, largest speeds. And the final one is the regular one, the average. So it looks kind of confusing, and the question is how the lower bound is obtained. Because if there is a simple lower bound and it is tight, maybe one can also analyze the power of preemption. So the lower bound, once again, consists of identical jobs, but the machines are not identical. Do I have a figure yet? So this is what it looks like. Maybe this is easier. All machines have the same speed of 2, and there's just one machine of speed 1. If all the jobs are the same, and we have m jobs, for identical machines, that would have been very easy. But here we have the problem on the left-hand side, that if you assign one job to every machine, there's a slower machine, and the completion time is double. And if you assign 2 jobs to the same machine that is faster, once again, you get the same completion time, because then you have 2 jobs. But for the preemptive schedule, here you need to be more careful. Maybe you see that on the right-hand side, the machine of speed 1 has a small piece of every job, and it is assigned very carefully on the other machines so that there will not be any overlap. If you look at the light blue job, it runs on the 4th machine, then moves for a little bit to the slow machine, which is the rightmost machine, and then goes back to another machine. It is not very important where the jobs run on the first 5 machines because they are identical, but on the 6th one, you need to be careful. Let me see if I skipped anything. So this is what the example looks like. And I'm not sure if I should say that this is well known, or maybe that Gerhard Wagner proved some of it, but I don't think there's anything else here. There's just a calculation or that this is the optimal preemptive Makespan, what you see on the right-hand side, and for the non-preemptive case, it is easy because they can't split jobs. And this is how we get a lower bound for uniformly related machines. For the upper bound, we do something that is similar but different from before. Earlier, for identical machines, we assume that there are at least m+1 jobs, because if there are m jobs, it is really easy. But LPT for related machines doesn't always assign 1 job per machine. It depends on the speed. If one machine is very fast, you would want to see all the jobs there. What we can assume is that there are at least m jobs. As I said, if there are less jobs than machines, you can remove a machine, and then you can use by induction the result for less machines. And this is not just some technical issue that we are not successful. Yeah, it's not a technical issue that we are not successful in proving that we need at least m+1 jobs, because in the example, in the lower bound, there were m jobs. So we need to consider the case that there are at least m jobs. And let's go back to the figures. Yeah, so the difference is that it doesn't look as nice as here, but the general calculations are similar. So here what you add is not P, but P divided by the speed. And if you add a job of that looks like P to every machine, it will not look as uniform as here because there are speeds. But still, there is a similar calculation that you can do carefully. You know that when P is assigned here, you know, to the Haifa machine, you know that assigning it to another machine would have gotten us a larger completion time for P. So you plug that in. Here, you just plug that in. These are very simple calculations. In the course, I would have shown all of them, but here is just to write all the properties and end up getting the result that you need. So once again, you bound in the middle of the slide, you bound L from above, and in the formula you have two things that are not dependent on m, which are the total size and the total speed, the sum of speeds, and you just use one bound on the preemptive solution. So even though there are so many complicated bounds, eventually you don't need that much. So this is not a very difficult problem. And let me say something else on Makespan. For two machines, I said that the tight bound is 1.5, but of course you could try to find the tight bound as a function of the speed ratio and not just to say that it is 1.5 or 4/3 for equal speeds. What about other speeds? So here is a result proved independently by two groups, Django and Ho, and Soper and Strusevich, showing that tight bounds can be on the power or benefit of preemption can be obtained. Here you see a graph, you see that the benefit of preemption starts, as we know, by 4/3, it decreases, and then it increases, and then it decreases again. Of course, it will tend to 1, because if one machine is really, really slow compared to the other one, you don't need to use it, no matter whether you are doing preemptive or non-preemptive. So this was on Makespan, and now it's time to move to total completion time or total weighted completion time. And here we can go back to one machine. In the beginning, you probably wondered why I wanted to show you this trivial algorithm for one machine. And the main goal was to show you later that one machine is not always that easy. So what can we say about this variant? For now, or for this talk without release dates. So upper bounds may be harder than before, because you're interested in all jobs and not just in one job that completes last. But there are some surprising results known, results for really many years ago, showing that for total weighted completion time, still the benefit of preemption is 1 if the machines are identical. And what I find surprising is not only that the actual result, but also that it was proved in such an early stage. Because usually if you have a look at papers from them, they are not very complicated. So here are some results that I was involved in. The first one is for one machine and release dates. This is the bullet in the middle of the slide. The work only contains lower bounds. The reason is that the upper bound follows from previous work and the lower bound is tight with that. So, sorry, here there are release dates. And the next one is the one without release dates. That's joined with Asaf Levin, Soper and Vitalis Strusevich. And here we consider the related machines, the ones that have speeds, but the simple unweighted case. And if you want to know where we got this number 1.39795, just this is not something we invented. This is what we found. So I like lower bounds, even though they are less useful than upper bounds. So let me talk about the lower bound in detail. And as I said, of course, there are release dates. So let me show you a very simple example of why preemption can add a lot of power. So there's just one large job. In the figure, it looks like it is two jobs, but it is one job that is preempted. It has size 2 and release at time 0. It can happily run from time 0 to 2, only there is also a very small job. And going back to my promise that sizes are integers, well, 0 is an integer, but I promised also that they are positive. It is possible to replace everything but by much larger jobs and keep my promise, but it is easier to think about it like that. So it has size 0, and it is released not in the beginning, but at time 1. So if you can be preemptive, you can stop the job of size 2, run this very short job. You don't even harm the large job because it has size 0, and you continue the job of size 2. And then the total completion time is 3, 1 for the short job and 2 for the long job. But if you're not allowed to preempt, you're in trouble. This, let me just say that this is an optimal solution because everything is completed at the minimum time that it can be completed. The release time plus the size. You cannot do better. But if here is the illustration for the non-preemptive case. So since you can't preempt, you need to decide if you run the large job before the small job or after it. These are the only 2 reasonable schedules because there's no point to delay anything else. And no matter what you do, the total completion time is going to be 4, either both are completed at time 2 or job 1 that has size 2 needs to wait and it is completed at time 3 instead of time 2. This is actually a lower bound on the benefit of preemption for this problem. One can improve it for the unweighted case, but we are going to talk about the weighted case. Since the improvement is not very interesting and I did not get very far with that, I'm just gave that up. All right, so how do you generalize it? Because I promised you, let's go back. I promised you a lower bound of E over E minus 1, which is 1.581 approximately. And I only proved the lower bound of 4/3. The reason is that this is not the example, but the example looks like this. Here, the large job doesn't have size 2, but it has size n. Maybe it's the same because n is the number of jobs. In that example, there were 2 jobs. So it is released at time 0, but there are many small jobs that annoy it. They keep appearing at integer times. So there is one released at time 1, one released at time 2, and so on. It is convenient to with the indexes that the large one is job n and not job 1. So what can you do? If you are preemptive, this is once again very easy. You just stop the large job for a second, run the tiny job and continue. And everything is completed at the minimum time and everyone is so happy. You can calculate the total completion time, or if you want weights, you can see in the bottom the total weighted completion time. In this case, every job completes exactly at the time that is its index. And in the bottom, I also multiply it by the weights, which I still don't know what they are. If you're doing non-preemptive, you're once again in trouble. You can't stop the large job. So there are n schedules that are reasonable. You can start with the large job and delay everything for later. This is the top schedule. Or you can let one tiny job run, then run the large job, and then on the remaining small ones. Or you can do 2 of them and so on. And these are the only reasonable schedules because you don't want to introduce idle time for nothing. Here is a calculation of the total weighted completion time for all cases. It is just technical, so in the top one, they're all complete at the same time n, and you multiply it by the sum of weights. In the second one job, one tiny job completes at time 1, and the other ones at time n plus 1, and so on. So in this slide, you have all possibilities. In order to prove a lower bound, we would like to assign weights so that all these costs are equal. So no matter what is done by the preemptive schedule, the non-preemptive schedule, you're in the same situation. So this required a calculation, which turned out to be reasonably easy. Even though I'm in a department of mathematics, my colleagues think that I don't know mathematics. So this calculation was sufficiently easy, and we got the following weights. So it is there are powers of some value a, and a is equal to, this is the second line, to 1 minus 1 over n. So why do we get something that depends on e? The reason is that this term of a to the power of n is something that tends to some number related to e. So as I said, the upper boundary was already known when we worked on it. It basically was not proved as an upper bound for this problem. It was proved for something else, but they designed an algorithm that imitates a preemptive algorithm, and this is why the result holds for what we need. So there are, for some problems that I don't mention, it just happens that the results are trivial in terms of something. I will not give you the details, but you have the slides. And for the remaining time, let me move to uniformly related machines. This is the work here on this slide. I said that I'm going to, the last two big bullets, I'm going to discuss one machine, and this was already done. And I would like to discuss uniformly related machines, the work with Asaf Levin, Ellen Sofer, and Vitalis Trusevich. Okay, I will be brief because there isn't that much time left. So the optimistic part here, and we were only doing total completion time, not the weighted one, but the machines have speeds which complicate things. So the advantage, as I write on the slide, is that there are two polynomially solvable variants, the preemptive and the non-preemptive ones, and they appear in textbooks and everywhere. And even, once again, I will say, and even students understand these algorithms. And so the comparison is based on two algorithms. None of the problems is exactly hard, but the algorithms are not as easy as the one of McNaughton. So what I keep drawing this figure for one machine, which means that if you already know what you assign to some machine, there's no reason not to use SPT. But you may preempt if it is preemptive and remove parts between machines. And for the non-preemptive case, you still need to split the jobs and partition them between the machines. So the first algorithm, the non-preemptive one, is the multipliers algorithm. You're probably familiar with it. For you. Here's an illustration with numbers. You find the multipliers that the sizes of jobs would be multiplied by if you assign them as the last job of a machine. This is, for example, here, there's a speed 7, so you will multiply the size by 1/7. If it's the second from the top, it will be multiplied by 2/7, and so on. And you find the best multipliers that you want to use, and you make sure that you multiply the large size by the smallest multiplier, and so on. This is one algorithm, and the other one, here's the staircase algorithm. That this is, of course, the non-preemptive, where you make sure that you always run the m smallest jobs, and the fastest machine will run the smallest job, and so on. And the reason is that you want to complete things as soon as possible. Let me remind you, there are no waits. So it is nice to have two polynomial algorithms, but the relation is not that clear. And for a second, for someone who's not familiar with it, you can think that it is just the same. But if you run it for the same input, you get that the total completion time is not the same, so it's not the same algorithm. So let me say something about the results. Unfortunately, there's no time for everything. So even the previous example already implies some lower bound. You just plug in the results of the algorithms, and if you're lucky, you have a good lower bound. But of course, we would like to find time bounds, and this doesn't happen by just being lucky. The problem is slightly more complicated. So let me show an example here for just two machines. If there are three identical jobs, there are actually two reasonable non-preemptive schedules. And which one is better depends on the speed ratio. So you can see one schedule on the right-hand side where all jobs run on the fast machine if it's very fast, or one job is on the slow machine. And we don't need to guess, we have an algorithm for finding an optimal solution. But if preemption is allowed, then already you still have an algorithm, but it already becomes ugly. I'm not going to read out loud all the formulas depending on S. But still, two machines are typically manageable. And it turns out that the worst case example is actually just with two jobs. So the time bound for two machines is based on the speed ratio 2 and two jobs of size 1. Does it always happen that jobs of size 1 are the most problematic? It doesn't sound reasonable, but so it happens that this is the case here. So there is, you can see it in light blue. Yes, we can prove that there is a worst case input with unit-sized jobs. And this makes things slightly easier for analysis. So this is true not only for two machines. And you can see how ugly it can get by this illustration. So basically, it seems that the worst case is with the jobs of size 1 that we can prove. And it seems that one fast machine and many slow machines should be the worst case. But this was not clear to begin with. And you saw that for a different problem, the opposite situation was the worst case, that one machine was slow and the others were fast. So some conclusions and generalizations. There are nice results for unrelated machines by Correa, Scutella, and Vershai, where they showed that the benefit of preemption for unrelated machines is exactly 4. This is the case that every job and machine have a time that the job takes on this machine, and there's no relation. There isn't necessarily some relation between these values. What else is known for total weighted completion time? There are some results, because the 4 was from Makespan, right? And there can be other variants. For example, once we talk about weight or without weight, the result can be different. And what I do want to say is that for the tardiness, there is a problem that we cannot get an interesting result. You can see the figure in the bottom. If the deadlines of all jobs are 3, if the problem is preemptive, you can complete them by time 3 and have tardiness of 0. But if this is not the case and you can't use preemption, there will always be a job completed at time 4. So the ratio is 1 over, not 1. 1 over 0, which is infinity. And in this case, the power of preemption is infinite, maybe not the best problem on Earth. Okay, so there are other nice problems studied where here we compare no preemption to an not infinite, but arbitrarily large number of preemptions, and you can compare, there is work on that, different numbers of preemptions, and you can try to find how many preemptions are needed for an optimal preemptive schedule. Here we know that for the problems that I considered, Makespan on identical and uniformly related machines, this is a linear number in N, the number of jobs. And this is it. Thank you.
Okay, thank you. Leah, I will ask the first question. So you are active in two communities. One is scheduling and another one is bin packing, if I'm right. So could you comment about similarities of these problems? So is there something that they share in common? Intuitively, one would say this is still the same problem, but obviously it is not, right? So could you a little bit comment on it? And I will unmute other people so that they can ask again, right?
So I actually do think that it is the same problem. So bin packing is when you have an unlimited supply of machines available during the time interval between 0 and 1.
Mm-hmm. Okay, so now if anybody wants to ask, you can unmute yourself. It should work.
May I ask about something?
Sure, go ahead.
If I'm right, the basic assumption in your problems is that the sum of processing times of all parts of a job is equal to the processing time of the same job before preemption. That's correct, yes? So my question is, what if this assumption will be not satisfied? For example, we will need some additional time to make preemption, which will increase the processing time of the all parts.
Okay, so some setup time.
Yes, something like setup, yes.
Yeah, of course, everything I said today doesn't work, and but of course, I know that it was studied for some problems, even for online problems, but I'm not sure how the results will change. So my guess is that for some of the cases, you will get similar results, but of course the numbers will not be the same, but the proofs will be similar. And for other cases, it will ruin everything.
Yes, because as far as I know, the most of scheduling literature related to preemptive scheduling concerns the definition of preemption, like in your case. So it means that the sum of all parts give, with respect to job processing times, the whole processing time. So because I'm working on slightly different kinds of problems, so I was curious whether you know maybe some papers on similar topic, but with another definition of job preemption.
So I'm not sure that I saw papers on the benefit of preemption. So this could be nice.
Not necessarily on the power of preemption. On different kinds of preemption than usually it is used in scheduling.
I definitely saw such papers. I mean, maybe if you mail me, I will try to look them up.
Okay, thank you.
Can I add something to this?
Yes, go ahead.
I'm not sorry. Yeah, back to the previous question. Yeah, we did some research a few years ago by just considering that when we just preempt jobs in order to transfer job from one machine to another machine, we have some transportation time.
So we've, yeah?
Yes, for transport. So for example, if you, preempt a job on machine 1 and you want to, process it on machine 2 for the rest. So there's some transportation time or travel time. So then we found out for some cases, the problem is NP hard. For some of them is not NP hard. So we have a work published in COR in 2014. So back to your question. So there are some research in that area. You can look for them. And then they are very interesting, because, it's just the complexity of the problem is totally different when the processing, the ratio between the transportation time and the processing time are different.
Okay, thank you. I can also add that I have seen in the real-time community when they make analysis, so-called response time analysis, they sometimes use the term price of preemption, or some specific papers are interested in the case when preemption takes some time. But it's not for synthesis, it is for response time analysis.
May I ask one question?
Sure, go ahead.
Okay, first of all, thank you for your very, very nice talk and very informative. I have a very simple question. What is the situation concerning the fractional variant? I can imagine that the power of preemption in that case is even higher, but are there many results in this respect, or what is the status?
One interesting case that I can think of is restricted assignment, where even though you can run parts in parallel, still the restricted assignment that not every job can run on every machine makes it uglier or nicer. It depends on whether you like it or not. But usually it's what I showed in the beginning, that it just ruins the problem. That the job is like split like that, but
okay. Are there any other questions? So if not, let me stop the meeting. Thank you for coming. And the next talk in 2 weeks will be given by Sir Federico della Croce from Italy, right? Federico is here, so I hope that you will stay with us, and we will meet in 2 weeks. Okay. Thank you for joining us, and see you in 2 weeks. Bye bye. And thank you, Leah.
thank you.